So to bring about a connection between pressure and the Lagrange multiplier, let's look at our flow problem as an energy minimization problem. So here I have written the FEM discretization which we showed in the previous video, and now let's look at how the energy minimization problem can help us connect the dots and tell us why we are multiplying the divergence free velocity constraint with our pressure test function. So to do this, in many textbooks or on the internet, you might see that the energy integral is written as something like half into mu into, which is your viscosity, into gradient of u, which is u is your velocity here, so gradient of u, double dot gradient of u. So let's look at how this integral comes about. So one way to think about it is that your momentum is basically just your mass into your velocity, which is of course a vector equation, and to convert it into your kinetic energy, which is a scalar, we can just do half into m into u dotted with this guy, right, which is basically just your half mu square. So let's just do this with our Stokes flow, and then we would just get this guy here, the integral which we just showed, and then we would be able to get this kind of our FEM discretization. So let's just start off with this, and I'll just write down the Stokes flow first. So our Stokes flow is our divergence of stress is equal to 0 integrated over the volume. So this is our Stokes flow. And then we have our constraint here, which is our incompressibility. And this incompressibility constraint modifies our mass balance, giving us del dot u is equal to 0, which is our continuity equation. So let's simplify this further. So let's multiply by half into, this is your velocity dotted with gradient of tau. So this is our viscous part, the viscous part of our stress tensor, and then our pressure part is u dotted with gradient of p. So you can see that this is our stress tensor dotted with the velocity. So so both of these terms are basically just scalars, right? So to understand this, one way is to use integration by parts, and to do that, so let's just do that. Let's apply integration by parts, and we would get something which is much more simplified. So this term you might have seen in your viscous energy dissipation. So if you look at equations for energy balance, you might see this term for the viscous heat dissipation. And then you also have this guy, which just becomes del dot u. And this is 0 because del dot u is 0, right, as per our incompressibility. So this guy goes to 0. And then you would of course have your boundary term, which would be just u dotted with tau, which is a tensor, dotted with the unit normal in the outward direction, minus u dotted with this guy, dotted with again the unit normal. So this is your work done at the boundaries. And this guy is basically your energy dissipation, which in this case it is Stokes flow. So this is just your viscous energy dissipation, which basically just means that the work done at the boundaries is what is getting converted in your viscous energy dissipation. So you could apply a pressure kind of boundary, right, or rather a pressure gradient, or even if you apply basically your a Dirichlet boundary condition, Dirichlet velocity is equal to some constant value. So this, so you could just get this integral again as a reaction force at that boundary by integrating the traction at the boundary and dotting it with the velocity. So So by doing that, you would again just get the work that is required for maintaining that Dirichlet boundary condition. So of course that Dirichlet boundary condition is also doing some work, so you could recover it in that way. But now let's simplify this to get our grad u double dot grad u kind of term. So to do this, of course, we have our simplified term from the incompressibility. So we know that in our Navier-Stokes equation, we can just simplify gradient of tau. I'm sorry, not gradient of tau, divergence of your tau as mu, your viscosity, into del square u. So we can just do that here. So we can just write this guy as mu into del square u, and then when you apply integration by parts, this guy would just become mu into grad u double dot grad u. So we have got this integral, and again here we just have gradient of u. Right. So of course we are using the incompressibility, so we get these two conditions, and so this is the integral for the energy which we want to minimize, and it is subject to a constraint which is again your incompressibility constraint. So let us write that down. So minimize energy, which is our half into mu into grad u double dot grad u, subject to the constraint which we have to maximize. So maximize the constraint. So this leads to a min-max kind of problem, of course. So, and our constraint is del dot u is equal to 0. So to do this by using the concept of Lagrange multiplier, so the way to do this is, first let us just write down this guy as an integral. So this only has one variable, and this is the integral which we want to minimize, the function that we want to minimize, and this is the constraint which we want to maximize. So to do that, we just write this as u dot lambda, where lambda is your Lagrange multiplier, mu grad u double dot grad u plus lambda into your constraint. So this is the constraint which we want to maximize, and this energy is what we want to minimize. So so to do this, we just take our directional derivative, which means we will just okay, so first let us just so to do this, of course, first we will have to just look at the perturbations. So we perturb u as u plus just a linear perturbation, u plus epsilon v, and then we also perturb lambda as lambda plus epsilon q, and then we can take the directional derivative of this guy here of I, in which we have done this perturbation as well as this one. So first we'll just do one perturbation, and then we'll do another one, and we'll just see the partial derivative, the directional derivative, right? The partial derivative with respect to epsilon at epsilon is equal to 0, right? And with this perturbation we should get a value of 0, and again with this perturbation again we should get a value of 0, right? So so once we do that, we'll get a solution which will be stationary, right? We'll get a stationary solution which by solving this min-max kind of problem. So so once we do that, so maybe I'll not just show the entire thing, but let me just just show what's happening here. So you have your half mu grad u plus epsilon v double dot grad u plus epsilon v plus this guy into del dot u plus epsilon v, right? And so let's simplify this term. So this term would and this, of course, you have this guy here at epsilon is equal to 0, right, which is being applied here, right, and we are setting this to 0. So to do this, so let's simplify this. So you can just write this as, we can just since this is linear, we can just break this, and once we do that and take this double dot, you would just get terms like grad u double dot grad u plus grad epsilon v double dot grad epsilon v plus 2 times grad u double dot grad epsilon v, right, and you would also have half outside and lambda into again this guy. And once we apply the partial derivative with respect to epsilon, so clearly this guy goes to 0, and after you apply epsilon is equal to 0, this guy goes to 0. So you are just left with and you have a 2 here, so you are just left with integral over the volume. So again you have an integral here, right, integral over the volume grad u double dot grad v into, of course, your mu, which will also be here, right, plus lambda integral over the volume del dot v, right. So we have this equation here, which looks very similar to our FEM discretization, right, the momentum balance for our FEM discretization. So now let's just do the second perturbation, which is with respect to this guy, and this lambda is really present only here, so this is more simpler. And so when you just take the partial derivative, you would just get so since the perturbation is lambda goes to lambda plus q epsilon q, so we would just get integral over the volume q del dot u is equal to 0, right. So this is very similar to our FEM discretization, in which v was our velocity test function and q was our pressure test function, and lambda is coming in the place of our pressure, right, the pressure multiplier, rather the pressure, right. So we can really make this equivalence here, that from these two equations, that pressure is just working in the place of Lagrange multiplier, but let's look at the intuition as well. So in the previous bunch of videos, I think the first bunch of videos, so we talked about the weighted residual statement, and so I'll just drop the link in the description. But let's try to understand this. So in FEM, we are just discretizing our domain into small finite elements, and we are driving the residual to 0 at each of these elements. And to test that the residual has gone identically to 0, we just use test functions, which are piecewise continuous functions inside each finite element. And we also know that by the fundamental lemma of calculus of variations, basically if your residual has gone to 0, you could just multiply it by any function inside, which is sufficiently smooth, continuous, differentiable kind of function, so long as it is just defined inside this. Outside this domain, it goes to 0. So you could just multiply by any kind of test function which is satisfying the continuity, differentiability, and it is just 0 outside. and you should get a zero value, right? So that is the essence of our weighted residual statement, right? So the test function is like a perturbation on this domain. Why? Because typically we are looking at non-linear kind of problems, in which we start off with a guess solution. So the residual of the actual solution, if u is us, which is your solution, then your residual inside your element, integral of the residual inside every element, would just go to 0. But we start off with a guess solution in most non-linear problems, right? Because we are mostly solving non-linear problems. So you could think of it as a guess value, and this would not go to 0, right? So what we are doing in FEM is we are just multiplying by test function, which is testing this our statement, and our residual inside the element, we are just driving to 0, and to do that we are just optimizing our or rather just varying our coefficients, right? And so this is our weighted residual statement. And so if you look at what the test function is doing, it is just perturbing your residual, right? And you're just driving that to 0. So this is very similar to what's happening here, because you have Q here, which is perturbing your Lagrange multiplier, and V, which is which is perturbing your velocity, right? And you also have lambda in place of P. You might have a minus sign here, so maybe you should just have a minus sign here, right? So, but really pressure is just determined up to an additive constant here, right? So really the connection is pretty similar. So you can understand that what you're doing in FEM with your test functions is really the same as you're doing here with your perturbations, and that brings about the connection between the two. And I hope it clarifies why Q, the pressure test function, is multiplying the velocity, the divergence free velocity constant, and why you have the velocity test function multiplying your gradient of pressure here. So so I hope this connection is clear, and I hope it was helpful for anybody who is new to finite elements. And really this is just the starting, and so we have something which is called as the LBB condition, which is the Lady-Zenskaya Babushka Brezi. I'm sorry if I got that pronunciation wrong, or it is also called as the inf sub condition. So this is more of probably finite element terminology, infimum and supremum, because we are solving, we are basically just minimizing this energy and maximizing this constraint. So to do that, really you cannot just use any kind of polynomials. So you can't just discretize pressure with, let's say, linear and velocity with linear, then it doesn't work. And so that's what we'll look at in the next video, because you have to satisfy this condition, and only if you do that you would get stable and convergent solutions. So let's look at that in the next video.